since this is our start to our problem, and we've established the negative charge density of the white portion of the atom, and that the blue part is simply a positive charge of positive ZE. When I look at what I need to do to get an expression for the electric field, I want to remind everybody that to do that, we need to break this problem up into two parts. There's going to be the part that identifies the amount of enclosed charge, and the part that's going to help us find the flux. When we talk about the enclosed charge, it should be evident that when we reach the outer edge of our sphere, out here someplace, the net charge should be 0, because we'll have an equal amount of positive and negative charge by then. And when we're at the center, the only charge we should have is the point charge. So we should have kind of this evidential idea that our final expression leads to something where the total electric field outside the atom is 0, and that's the expression they've given us. If you look at that expression carefully, you realize that when little r equals capital R, that expression goes to 0. Because the one that they gave us, they told us what our answer is supposed to be. They said that the electric field has to be 1 over 4 pi epsilon naught times, ZE up here, so ZE, all times 1 over r squared minus r over big R cubed. That's our expected answer. That seems not unreasonable. So, ready to begin? I'm going to start with the Q enclosed portion, because I think that's the part that's probably the, the one that I can kind of just see here and kind of express. To get the Q enclosed, I need to know that I'm always going to be enclosing the positive ZE part. So this is my Q enclosed. I'm always going to be enclosing that, but I'm also going to be enclosing some amount of negative charge, which I'm going to get by multiplying rho times the volume. Now, rho is our charge density here, and the volume is the volume enclosed by my Gaussian surface. So this is going to be Q enclosed equals positive ZE minus ZE over 4/3 pi capital R cubed times 4/3 pi little r cubed. That's my charge enclosed. And of course, you've probably come to expect this if you've been doing any of these or have been at least keeping up with me when I've been doing some of these, that the 4/3 pi cancels out here. And I'm left with positive ZE minus ZE r cubed to r cubed. Any questions about that? This has all of the qualities I expect. When r equals 0, I have just positive charge. And when r equals capital R, I have no charge. So it has the expected shape and size that I would want to see. I'm out of space here to continue. So I'm just going to tuck this into my brain for a minute. And for just a moment, I'm going to contemplate the flux before I go to a clean page. The flux is going to be E dot dA. And just looking at this, can we all make the agreement that the electric field is going to be in this direction, radially outwards? It might be radially inwards, but I think there's going to be more positive than negative charge until we get to the edge. So I think we're talking radially outwards. And at the same time, I'm expecting there to be my area always perpendicular to that surface, should always point in the same direction as the electric field. Are we good with all that? Well, Devon says yes, so we move on. So I think we just have E times 4 pi r squared. Still just a sphere. Now, this just looks like a fever dream nightmare right now, so I want to go to a nice, clean, fresh page and bring it all together. So Q enclosed equals epsilon naught times flux. So Q enclosed, ZE minus ZE r cubed over r cubed equals epsilon naught times E times 4 pi r squared. So we need E by itself. I have to clean this up a little bit. And I don't know how you guys feel about what I'm about to do, but I'm going to factor out the ZE and put it over 4 pi epsilon naught. Inside here, I'm going to have 1 minus r cubed over r cubed. And on this side, I'm going to have E times r squared. I'm doing this in 2 steps because I did a bunch of factoring and everything. And I want to make sure that I'm not doing too much algebra to lose some folks. Am I okay? I just divided both sides by 4 pi epsilon naught and factored out ZE. Because now I'm going to divide both sides by r squared, which gives me, ZE over 4 pi epsilon naught 1 minus r cubed over r cubed and now to make it look like the one that we had, I'm going to distribute the 1 over r squared. When I do, I get 1 over r squared, and I cancel out the r squared with 2 of those r's. And that's how we get it. So that's the electric field. And so 92 times E, I'm just going to make this nice and big. E is 1.6 times 10 to the negative 19th coulombs. E is the charge in the electron. So all that divided by 4 pi epsilon 8.85 times 10 to the negative 12th times, and just bear with me for a minute, it's 1 over half of r squared minus half of r over r cubed. So I think we can kind of do some stuff in there to simplify. And that's what I'd like to do. Because it looks like the one on the left is going to be 4 over r squared minus, and the one on the right is going to be 1 over 2r squared. So if I got common denominators, that would be 8 over 2r squared, which means the whole thing is 7 over 2r, which is, r is 0.1 nanometers, or 1 times 10 to the negative 10 meters squared. All right. Well, it looks like a lot of fun, but that just looks like a calculator. So I think we've done all that I feel like doing. But Alex probably would have done all this just fine on his own, so I'm wondering why he's asking the question. There must be something I'm missing.
No, I completely forgot. I only plugged in 92. I completely forgot to turn it.
Oh. Okay. Well, I'm glad that we got that together. Glad I was able to answer your question, and I hope I answered the question of anybody else in the room who's having difficulty with this problem. Do I think this is a testable problem? Yes, 1,000% yes. I see there's no problem with putting this on a test. I'm not saying it is. I'm just saying that to me, especially since I gave you the electric field, which meant you could do B and C on your own without having to do any of the Gauss's law stuff, I'm okay with it. About any of those pieces. I'll say it again. Let's just label this so we have a label. At point A, I am inside the charged shell, so any charge on the charged shell is not contributing to the electric field at point A. However, the charge on the inner sphere, that charge can be treated as a point charge because we are not inside the sphere. And we know all of its residual charge will be on its surface anyways. So when the question says, what is the charge on the surface of that sphere? It's redundant. We know it's all on the surface. We don't have to do anything though but treat it like a point charge, which means my electric field can be simply equal to Q over 4 pi epsilon naught times R squared. I can treat the whole thing like a point charge. The fact that the electric field is towards the center means the electric field is negative 15,000 newtons per coulomb. And my 8 centimeters needs to be in centimeters. I'm sorry, in meters. So it seems to me we're just a short calculation away of figuring out what the charge is on the inside sphere. And I never have to use the 5 centimeters there. So I'm going to continue, but I expect that charge to be negative is my answer. So we'll get 4 pi times 8.85 times 10 to the negative 12th times 0.08 squared times negative 15,000. I have no idea what that is. 2.1 times 10 to the 16th? I don't know. Maybe negative 16th. Right? But I don't think so, because I think just looking at the powers of 10, I've got times 10 to the negative 12, times 10 to the negative 4, and times 10 to the 4th. So I'm thinking it's going to be like times 10 to the negative 12th, or near that.
My question is slightly different.
Everybody's question probably has a slightly different value.
I got negative 11.4 and negative 2.
Okay. So everybody's numbers are a little different than these. What'd they change? The electric field?
That was 16,000.
So when they're going to vary one number, I thought I went through and unchecked all of that, but clearly not. So I don't think this is, we need to battle this out. This is just punching numbers into your calculator. I know that is something that mastering does not make easy on you, but do I need to explain any more of that? You guys at home okay?
Mr. Sean, why'd you put negative 15,000?
The electric field is pointing into the center from that point that's on the outside. If I was to consider for a moment the way the Gaussian surface would look, if I backed up to deal with that, remember that we would have E dot dA in there. This dot product would produce a negative sign because my electric field points inside while the area points outside. That would create the negative sign that would stay with the electric field. We also have, from way back, like first 2 weeks of school, the fact that the true definition of the electric field is Q over 4 pi epsilon naught R squared times R hat, where R hat is a positive vector that goes from the charge to my location in space. Since my electric field is in the opposite direction, I have to list it as negative then to indicate that it's back towards the original charge. Does that help? Okay. Keep going? All right. So all of you should have a number here, and we'll just put an I here to indicate that's the inside charge. We're going to need that. Because the next question asks B, the inside surface of the hollow sphere. To get to the inside surface of the hollow sphere, I would have to assume a Gaussian surface that is now 10 centimeters away. But, and this is the problem, do I know how much charge is there without having to do much work? And I think the answer is yes. Because I know the electric field in here has to be 0. So if I am just inside the shell, I know my total enclosed charge has to be 0, which means Q on that inside surface has to be equal to minus QI. Whatever the charge is on the inside sphere, I have the opposite amount on the inside surface of my shell. Any question about that? Okay, so now I can go to the final portion of the problem, which, believe it or not, is not going to change hardly anything here. The final portion of the problem is to find the charge on the outside surface. Now, to do that, and here's where I need to be kind of a little cognizant of what I'm doing. I don't have to change very much. I can go right here, erase that negative sign because the new electric field is positive 15,000. I can go right here and put in that I am 17 centimeters away, so 0.17 meters. And I can find a new expression for the outer charge, but it's not really the outer charge. What I will be finding is the total charge enclosed. That's what I'll be finding. Now, I can use this to figure out how much charge is on that surface, but what I'm going to get here is the total charge enclosed. And that's going to be 4 pi epsilon naught times 8 point, oh wait, can't do that and put the number at the same time, 8.85 times 10 to the negative 12th times 0.17 squared times 15,000, or whatever your electric field was. Now, that's the total charge enclosed. Can I go to another page where I can get some clean board to write on? Are you guys good for me to go someplace else? Q enclosed has to equal Q on the outside of shell plus Q on the inside of the shell plus Q on the inside sphere. So if you want to find Q on the outside of the shell, you will have to solve for it. We solved individually for this. This was part B. This was part A. You got to do some addition. Questions about that? All right. So if we already know that we have an expression for the linear charge density, we can bring it to bear on this problem. Now, if you'd prefer, I have no trouble running the numbers and doing Gauss's law for this real quick so we can prove where it comes from. Would you benefit from that experience? Actually, how should I say this? You guys should be able to do this. So how about we do it that way? You take a moment and derive this expression using Gauss's law. Not determine, derive. Meaning beginning with Q enclosed equals epsilon naught times the flux. Can you turn that into this? I'll wait patiently 5 minutes, and then I will ask one or two of you to provide me with the instructions necessary to get there.